undefined, so that wasn't helpful. So we're factoring. We can do a little canceling here. And we're left with this. But when we still plug in, we're still undefined. So we got to go to choice. Level. What is that? That's pretty. All right, so this is the pretty color line. All right, so sign chart. Sign chart. So we pick something to the left of -3, close to it, like -4.
-2.
We get a negative over negative is a positive. We pick something over here, like
You get a negative.
-2. We get
positive.
negative over positive, which is a
Negative.
negative.
And their opposites are P and E.
So it does not exist.
Wait, why does -3?
Can't use -3 because it makes the denominator 0.
Well, what if you didn't factor that?
Yes,
Is
ma'am.
there a difference between does not exist and undefined?
There is a difference between does not exist and undefined.
Oh, wait. I see.
The function at the value of -3 is undefined. The limit as the function approaches -3 does not exist. So the limit does not exist. All right. Yes.
I plugged in -3 and got 0/18.
This should have given you 0. Because when we plug in -3 here, we get 9 minus 18 plus 9. Yeah, so that should have been 0. All right, this one. All right, so I plug in 2, and we get 8 minus 24 plus 24 minus, we get 0. Okay, so step 2 is to factor. Now, the denominator might scare you. Don't let it. The numerator gives you a hint.
Oh, wait, can you do the backtrack? Can you backtrack? Well, actually, we'll just
We could just group it.
All right, so then back to what I was saying. The numerator gives you a hint. It's easier. So I'm starting there. So if anything's going to cancel out, I know it can't be the 2 because the first term doesn't have a 2. So maybe it's the x minus 2. So I'm going to kind of rearrange things so that I see that if I pull out a -6x right here, these two together would give me an x minus 2. I said 6x, I wrote -6. Try again. So I said if you pull out a -6x, you're left with x minus 2. We good? All right, so I'm doing grouping, but I'm going to group it differently. So hopefully you notice this is a difference of cubes. Do you see it?
Yeah. Oh, it's like my.
Okay, so difference of cubes is going to factor to x minus 2 times x squared plus 2x plus 4. All right, so both of these have an x minus 2 in common. So I'm going to pull it out in front, and I'm going to group everything that's left. All right, so this gives me x minus 2. And this is probably y'all gonna have a little bit of excitement right here. Because what does that factor to?
X minus 2 squared.
X minus 2 squared, so this becomes x minus 2
Oh.
cubed. Because there's 2 right here and there's another one right there.
Sounds good.
It's actually really satisfying.
All right. So, let's see if this helps. Man, that didn't help.
Oh, I'm
Because
unsatisfied.
still, when I pull in the 2, I got a 0 in the denominator. So now, even after all that work, even though it was happy work,
Got Frank.
I still have to sign chart it. Alright, so we'll throw a 2 right here. Now the cool part is what's squared, what's left is squared. So no matter what I plug in, it's going to be positive. So we got a positive, we got a positive, we got a positive infinity.
Oh my goodness.
How are we feeling? Alright. Okay, so let's take a look at number 9. Alright, so I would be scared, but when we started these, didn't we start with piecewise graphs? And were they pretty easy? Wasn't this just a piecewise graph? And we kind of have an idea about what these are. We know this is a parabola that's been dropped down 4 units. And so the whole thing would look like this. But we only get to start at 4 right here. Right? So let's make that part go away. Erase. Not at 4. We start at x value of 1. So we know the vertex would have been right there. Dropped down 4 units. Okay, we know this one, it would have a y-intercept here at -1 and a slope of -2, so I'd go this way, but it would come to 1 and it would be an open circle. Huh. So really they connect, because this open circle went over the closed circle, didn't it?
So that means they're both whatever that is.
Okay.
From left and right.
Alright, so I can see it. I can see it already. Alright, let's go through our steps. Can we plug in 1? Yes. When we plug in 1 into the top piece of this piecewise equation, we get out -3. When we plug in 1 into the bottom, we get out -3.
So let's negative 3.
But it says x has to be less than 1.
It does. But when we do a limit, we're looking at what it approaches. So yeah, we can't actually equal, but as we approach 1, what y value is your function approaching? You're right, it can't equal 1. But what is it approaching? Well, as we go towards 1 from the left, it's approaching -3. So, the limit as x approaches 1 is -3. Yes, sir.
If the top equation was just greater than 1, would it still approach -3 but be d?
Yeah, it would. Because the limit is what it's approaching, not the actual value of the function at that given x value.
But it would still be a d and e for the whole thing.
Nope. If this were just greater than,
'Cause would
your
you
graph
choose-
would look like this.
would you-
If both of them had no equal to, your graph would look like that.
Oh, you can still have an open circle.
Mhm.
That's where they can-
Yeah. Okay. All right. This one. The limit of the function as x approaches 2. Oh boy. All right. So I've got things that I need sign charts for, don't I? Because I've got undefined values when I plug in 2 and nothing factors. So I'm going to need a sign chart. So on the right side over here, I'm going to use that top function, right? So as we get, let's try 3. We get 3, we get a positive over a positive, which is a positive. All right, over here we got to try something less than 2, 1. We get a negative over a negative, which is a positive. So what are they approaching? Positive infinity. Yes, sir.
And so the limits right there are just there, so like, oh, never mind.
Okay. So we have to pick our approach. All right. Here's the next one. Isn't this the next one?
Yeah.
All right. So the limit as x approaches 0 of this. Okay.
Wait, it's x plus.
It was?
Wait, it's x plus 2 hours. What?
X. Okay. And what's the denominator?
X, yeah.
X. And what is this?
0.
0. All right. So, if we plug in 0, we have a problem. Nothing factors.
So it's not.
But, alright, let's see.
There's no.
Only vectors and it's 0 models regardless center.
Could we rearrange this? Could we do anything to eliminate this?
Multiply everything by square root.
By root 2, and then it'll just become 2.
How about by the conjugate? What happens when we multiply something by its conjugate?
Middle terms.
The middle terms cancel out and it gets rid of all my radicals, doesn't it? Alright, Mobius is not happy today. He's like, isn't it the end of school yet? Shouldn't you be putting me in a box and going someplace fun? I agree. Alright, so if we do this, we get x plus 2. And we get minus 2. Aww. And then we get x over this stuff.
X times x.
And so we get x over x times that stuff. Did that help?
No.
No? Don't these cancel?
Back in.
What the heck? Oh, yeah. How'd that happen? Wait, where did the minus 2? Oh. Oh, yeah.
It's still 0.
Yeah, sign chart.
Oh no, it's not 0. It's not 0 because it's root 2. It's going to be root 2. Wait, no, it's not.
Why don't you just like?
Wait, if x equals.
Can you square everything now, or is that too much?
As long as
Plug in
you're
0.
multiplying it by x.
Can we plug in 0?
Yeah.
Yeah, you can.
Yeah. So if we plug in 0, what do we get?
2 root 1 over 2 root
You get 2 root 2. You're supposed to bring out my mouth.
But-
That's wonderful.
Never mind.
Oh, so is that just,
Interesting.
That's your answer.
Alright, let's pull out, do y'all have Desmos? Let's take a look at this. Where's all my math stuff? What is it?
Oh, this is so weird.
Is it fun?
You want to know why?
That's so funny. I'm so sorry. Just kind of stops. So then,
Yeah,
so
but
then
then
it's not a
it's
pressure.
And I did do this again. It's on mine. The answer.
What value were we given? 0?
Yes.
Alright. Okay, so right there, it is undefined, which we knew. We knew to start with, remember? Because when we plug in 0, we got something that was undefined. Okay? But let's take a look. Just to this side, look at our value. Just to this side, look at our value. Punch into your calculator. 1 divided by 2 root 2.
I see it better when you graph it.
Okay, I got 0.353. Does that sound reasonable looking at our graph here? 0.353? Yeah, it does.
Is that
Okay.
I started off with those.
All right, now, the next ones. All of these look like we're trying to find the limit, at least the top three, 12, 13, 14, the limit of a rational function. Okay? But these, we're looking at the limit as it approaches positive and negative infinity. All right, how does that connect to the graph? That's the same as the end behavior, isn't it? As we look at positive and negative infinity. So, we're looking at what we approach. Yes. So, this is going to tie back into what you already know about end behavior rational functions. So, if we're looking at the limit of a function as it approaches positive or negative infinity, remember, if the highest power of x appears in the denominator, the limit of the function is 0. Do y'all remember those? So if we had, for example, y equals 2 over x. Do you remember what this graph looks like? Zoop. Zoop. Y'all remember those? Okay. So what's happening as we go towards positive or negative infinity is it approaching the x-axis, so the function approaches 0. All right? If the higher power appears in the numerator, if it's top-heavy, then it will either approach positive infinity or negative infinity. And finally, if the highest power, if they're equivalent, if the powers are the same, remember we do the coefficients. So when I gave you ones like this and we were looking at end behavior, if I said the function was 3x minus 1 over 2x plus 5, the end behavior would be the function approaches 3/2. Do y'all remember that when they're the same? Okay. So we got similar stuff going on here. Now, this is as it approaches positive or negative infinity, not the other values, as it approaches positive or negative infinity. All right, so for this one, we look at this. We're looking at as it approaches, is that positive infinity?
Yeah.
Okay, so the exponent of the highest power, numerator smaller than denominator. So if the highest power is in the denominator, it is 0. All right? Highest power, they're the same. So as it approaches infinity, it is 4/5. All right, top heavy, larger one in the numerator. Okay, the larger one's in the numerator. So what it says to do on this one is plug in very large numbers as it approaches positive infinity, or we would plug in very small numbers as it approaches
Does it mean like
negative
decimal
infinity,
small?
and see what happens. So if I plug the big number in here, 100. 100 cubed would be 3, 1, 2, 3, 4, 5, 6.
23 doesn't have a chance.
Okay, minus 23 over 399. Is it positive? Okay, is it pretty big? Okay, so that is approaching what? Positive infinity. Positive infinity.
This will be, do I have the right positive infinity?
Positive infinity, yes. Okay, we get the idea? Okay. Here are some other notes. So let's take a look at some different examples of other limits, and I'm going to tack these onto the end of your notes when I post them, so you don't have to write them down. What can we do with things like this? We've got undefined, all right? And so algebraically, could we simplify this? Yes, we could.
You can multiply it.
Okay? So conjugates come in handy when we have radicals, because conjugates help us eliminate radicals, right? So when we have this radical here, we can multiply the numerator and denominator by its conjugate, and we've eliminated it. And when we did, a really cool thing happened. Look what was left in the denominator. 9 minus x. What was in my numerator? 9 minus x. So what could we do with those? They can cancel,
It's 6.
and the limit is 6. Okay, so sometimes we can simplify, we can rewrite, such that the part of the function that makes it undefined when we plug in that value cancels out. Just like we did a minute ago with a radical. Yes, sir?
On a graph, would that be the actual value, or would that still be on the
That
That's where they both meet.
It would be an open circle,
Okay.
but it would be where they're meeting. Kind of like it was, I didn't snip it, did I?
Where, how do you know so?
Kind of like it was right here. Wait, where is it? There it is. So that was the value at 0. The value at 0 is defined, but what is the function approaching?
0.
It's approaching that 1 over 2 roots of 2. The value, this, we can determine that y value. Yes, sir?
I'm not sure if you explained that, I just forgot about how do you determine it's open or closed circle?
Well, I know there's a hole right there because this is undefined at 0.
Okay.
So
Yeah.
I know there's a
So on
hole
each
at
side-
0.
Okay, yeah.
So when I think about this graph, I know there will be a hole at 0.
So when it's not a hole, that's when the very first step works, right? When it's solid.
Yes. Okay. This is almost the same as the other one, except it's just negative. Okay, so when we plug in a 0, we get the undefined. But we can simplify this or rewrite this such that the part that makes it undefined can be eliminated. And when we do that, we can plug in the 0 into what's remaining and find that value. And so what that value is going to represent every time, I didn't save it, what that value represents is the y value that the function approaches right here where it's actually undefined. What is the y value that this function is approaching? Because that's what the limit represents. The value that the function is approaching. So the function is actually not defined for that value, but we can tell what it's approaching.
0.325.
Okay, this one, we got to get a common denominator here, right? So if we had one like this, we would get the common denominator by taking this first fraction and multiplying by x plus 1 over x plus 1. And then this simplifies to x minus 1, which cancels. And we have eliminated the factor that made it undefined so that we can find the value that the function approaches.
What if you messed up and you didn't? Would it just not work if you tried plugging in after canceling out x plus 1 and x plus 1? Oh, you can't because there's addition in the middle.
Right. So we should always simplify this part before we try to evaluate. So really, I guess there's a part 1a where you have to simplify your function before we plug in. All right, and finally, when we have it raised to a power, that just means reciprocal, correct? And so we have to simplify this function. So we're going to get a common denominator. Then we simplify the numerator. The h's end up canceling here. And then when we plug in, we can actually evaluate. So, part 1a would be to simplify your function. Okay, that is it for today. All right, if you guys can continue to work on that second sheet I gave you yesterday, I am actually going to check it for those of you that will be here tomorrow. We'll look at it tomorrow. For the rest of you, I will see you Monday because many of you are taking AP US history tomorrow. And we will, I'll get you caught up on Monday. Yes, ma'am.
This entire thing done by Monday?
That's what we should be working on.
Wait, so just the rest of the front side?
Mm-hmm. And good luck to y'all this weekend. Oh, real quick advice. Saturday is all about you because it's prom day for my juniors and my seniors. Okay, so Saturday is all about you. But don't forget, when you wake up Sunday morning, it is Mother's Day. So, go home tonight, write Mom a sweet little note, put it on your dresser, so Sunday morning when you wake up tired and grumpy, you just go give her a hug, hand her the sweet note, and you'll be safe. Okay? That's how you're safe. Because I know Saturday is all about you, and then Sunday you're going to wake up tired and grumpy because you're normal. All right.